Now we're going to look at a couple of different ways to optimize an already parallel execution. First, we're going to look at an old trick that we discussed already when we just talked about caching. We're going to talk about cache waste. So the example we discussed back then was at a nested loop where we have an outer loop, and inside the outer loop we have two inner loops, where the first inner loop touches a giant data structure that's larger than the second level cache, and the second loop touches a smaller data structure that's smaller than the second level cache. So after we have just touched, executed the red loop here, y will of course reside in the cache. Now we go back again and we execute the blue loop. The blue loop is larger than the cache. We will kick out the red data from the cache, and now when we execute the red loop again, we will have to bring in that data and we will create cache misses. So what we realized back then was that the more optimized way to do this would be to use an instruction called prefetch NTA. The NTA stands for non-temporal access. So when we use this kind of instruction, well, we prefetch the data. Actually, we're not using the prefetching here because we have a prefetch distance of just one instruction, so we're not using the prefetch feature. Instead, we use the property that this prefetch NTA tells the memory system that this is a data with poor temporal locality, no temporal locality. So that tells the memory system that whenever when you execute the red code, as you always have done before, we just keep bringing that data into the cache. But when you execute the blue loop, we'll use the prefetch NTA, and that means when we're going to bypass the second level cache. So we're bringing the data to the first level cache, but when eventually that data gets evicted, it's going to be evicted straight to memory and will never put the data in the L2 cache. So now it will have the effect that we will always hit in the cache for the red data. We will never hit for the blue data, but we didn't do that in the first case either. So what kind of misses do we avoid by this kind of feature? So it's the capacity misses. The cache was too small to hold both the blue and the red data, but since we changed the code to not put the blue data into the cache, now we can actually get some avoid some of the misses, not all misses, of course, and the misses we avoid are capacity misses. But of course, as we also discussed, this is beneficial not just when you execute a single code, but even more so when you have multiple threads sharing a cache. So here we have an example where we have multiple threads sharing cache. We have the red job being done, performed by this yellow CPU, and the red job has a miss ratio curve that looks like this, so it fits in the second level cache. While the blue job is an application that needs a lot of cache, so it won't be able to fit all its data in the second level cache. So what we did here, as you may recall, Andreas Sandberg had a way to automatically do this analysis of the miss ratio curves of each application and automatically make necessary changes. So the red application, we don't need to make any changes because it already fits in the cache. So it will do the normal thing and put its data in the second level cache on eviction. While for the blue execution, we will identify the instructions that touch the data that has a locality which is outside of the second level cache size. So these are sort of the instructions that makes hopeless accesses to data, and we will change those accesses to prefetch NTA. So we will make sure that those accesses are not being put in the second level cache. And by doing this, as you may recall, we managed to automatically improve performance on 3 applications that were co-scheduled to run together. The yellow bar is the performance they have when they run one at a time and own the entire cache. The blue is the performance, here lower is worse, the performance they get when they are run together and fight for for the L2 resource, and the green bar is the performance after we have done these automatic modifications and automatically inserted the prefetch NTA, so you can gain quite a lot of performance here. Now we can look at some pseudocode of parallel execution and see or look at some fairly trivial transformations you can do to avoid some of the extra traffic that may occur in the system due to these kind of access pattern. So what we have here in this pseudocode is a pattern thread that initializes some variables, and then it spawns off a child, and the child and the parent will do the same thing. They will both go through a some huge loop with large number of iterations and do some work, and then they increment the counter just to see how many times they've been going in the loop, and then after the child ends, then the parent will put the total number of iterations that they've done together as being the variable A. And here a couple of assumptions I'm making in the pseudocode. One is that when you spawn off a child, the child will inherit all the memory that the parent has set up, so will inherit A, I, and total. However, since the child declares I as a local variable itself, this will actually be a thread local variable. So these two threads will not share the variable I, but they share the other variables. So looking at this code, we can see that while it's going to be executed correctly, it's going to create lots and lots of traffic. And the kind of traffic that will be generated is due to this increment of the variable A. So each time you increment the global variable A, so this assumes it's been volatile declared, you will create create lots of traffic here in the coherence protocol, because you need a modified, you need to put this cache line into state modified, and the way to do that is to invalidate all the other caches. So you will sort of get a ping pong effect here, where the variable A will be ping pong between these two threads here. So that's not a very effective way of doing it. A smarter way would have been to create a thread local variable B and increment that variable here, and at the end of that that loop we set the global variable total to be equal to B. This thread over here will wait until this child has ended, and then right after that it will just add the value of A to total, and you will get the same result. So this would not create any coherence traffic here, no, since now each thread would have its own local variable. So what kind of misses are removed when you make this kind of optimization? So it's coherence misses, and actually the title of this slide was avoiding coherence traffic, and I just hid it from you to not make this too easy. So this is coherence traffic that's being generated, and there's what's called the coherence misses in the caches. You miss in the cache because somebody else invalidated you between two accesses to the same piece of data. So this is and it's very easy to make these kind of mistakes, especially if it's the code looks pretty much the same as before. And what may confuse you even more is if we look at the next example. Here, actually I didn't take away the title. I say avoiding false sharing. Here I have almost the same piece of code as before, and I claim that this is not a very good code. We have one variable here which is updated by the left thread, and a different variable that's updated by the right thread. Still, this would create as much traffic probably as would the unoptimized case of the previous slide. So take a look at this code and see if you can figure out what needs to change. So we need to change the declaration of B. So here, B, even though B is only used by the child, it's being declared in the parent, and that could be semi-okay. Problem is that A and B are declared right after each other, and that means that they are very likely to reside in the same cache line. So typically, the data is laid out sequentially in memory in the order that it's being declared. So unless you're very lucky, A and B will be in the same cache line. That means that even though these two threads don't share the variable A and the variable B with each other uh, um, inside the loop, it will still be this ping pong going on, this thing called false sharing, because we keep cache coherence with a cache line granularity, not with a variable granularity. So what you would do, one example of what you could do would just be the same solution as the previous slide. You declare B to be a local thread local variable in the child. Another way to do it would still be to declare B by the parent, but to make sure that A and B are far apart enough that we could guarantee that they don't reside in the same cache line. One way to do that would be to use some kind of alignment primitives that is supported by many compilers, where you say, and now when I declare the variable B, make sure it starts with an alignment of 64 bytes, at least that away from A. So you can have statements sort of advancing the next space where you allocate the next variable. So one thing, just pulling things apart sometimes is called padding as well, and that is often used as well to avoid false sharing. But this is, of course, with the thread local variable is much nicer way to do it. Finally, I'm going to just look at an example which I refer to as a coherence utilization problem. So here we have a slightly different example where we, in the parent, we go through a vector of a struct, and then we update just one member of the struct. So we update all the A's for all the entries of this vector X. And once we have incremented that, then we spoil a child, and the child is going to use exactly those values. So once more, since when you have this kind of vector of struct, the way you lay out the code is first to X sub 0, it's going to have all these variables, and then X sub 1, not 12, sub 1 is going to have all its variable laid out in memory like this. And this communication means that we're going to have to transfer all these cache lines over to the child, even though we're only interested in a single member of the cache line. So that will create 5 times more data movement than we would have needed. So a better way to do this would have been to make a vector just of A and incremented all the entries of that vector, and that means we only need to transfer the 5 times as little data, 5 times less data when we execute this code over here.